Hello everyone, my name is Talysson, and today I'm going to talk a little bit about functional programming and more specifically about what is the bare minimum to grasp it. So the first question we got to make and get the answer for that is what exactly is functional programming? So the gist of it is that functional programming is a programming paradigm where the base units are functions. And okay, that's actually it. Thank you for coming to my TED Talk. No, just kidding. So functional programming is a paradigm where the base units are functions, but it doesn't mean much, right? I mean, what is the difference to other paradigms? What is the advantage of using it? How does it even work? So let's do a small comparison first to know what actually is the differences. So in object-oriented programming, or OOP, we have data and behavior in the same place, and we give actually we call the data state, and we call the behavior methods, and we give the cute little name for those buckets of data and behavior as objects. And every time we need an object to talk to another object, at least the original thought for that was that an object sends a message to another object, and nowadays we just call it that it's a method call. So an object calls a method in the other object, and following this flow, the other object is going to change its own internal state, and then going to response it. That's going to return it through a response. So OOP follows the request response model. And even though I know it sounds kind of silly having to say that, remember that people even created a type of diagram to represent this kind of communication called sequence diagram, because of the fact of this request response model, it can get out of hand. So, okay, we know how objects talk to each other, but what if we need one object to be composed to another object? What we need, we have behavior in two different objects, or state in two different objects that we need to interact. What we need to put them in the same place. So, of course, we create another object. And again, I know it may sound silly, but it's also another thing that sometimes can get out of hand, and people created another kind of diagram called class diagram to represent that. Okay, so we now know how OOP usually works. What about FP? What about functional programming? So in functional programming, we separate data and behavior in two different places. And actually, instead of behavior, we call it functions. In OOP, people invented UML to be a way to describe the language, to describe the practices and how everything is meant to work. But in functional programming, everything is described by math. So there's a field in math called category theory that tries to explain the relations between categories and morphism. So we can relate it to functional programming, saying that data are separated by categories and the functions are called as morphism in category theory. And there's another functional programming thing that people talk a lot about, which are functional composition. This is also something that is covered in category theory. You can have morphism composition the same way you have function composition. And okay, so different from OOP, where you have a request response model, in functional programming, you actually have a model similar to pipes. So you send data through one of the ends of the pipe and get data back in the other end. There are no internal state, there are no side effects or stuff like that. And what happens if you need to compose behaviors? What you have three different behaviors and you want to make them talk to themselves. You just plumb them. You just plug all the other functions together in a way that pipes would do. Okay, but what makes it actually different? I mean, I can do all of those in OOP as well, right? Well, you can, but if you're using OOP following approach purely functional, you're probably using the wrong tool for the job. It's not what OOP was invented for. And so what's the core factor inherent from functional programming that makes unique? What makes it different? So I'm going to begin saying that it's purity by design. So functional programmers talk a lot about purity and pure functions all the time, and let's say they just can't help themselves, right? And can you blame them? Functional purity is something that's pretty cool, so I'm going to do the same, and let's talk about pure functions. Okay, so pure functions. A pure function is a function that is deterministic. So given the same input, you always have the same output, and some people can say that they're the same thing, but you can have deterministic functions that are not pure. Determinism doesn't stop you from having side effects. It just says about the input and the output. And the difference between deterministic functions and pure functions that besides the fact they are deterministic, they also don't modify anything outside of itself, so there are no side effects. And because of that, they're easier to compose because they're simpler. And pure functions have no access to variables, only immutable constants. So I put here 3 small examples of pure functions. So I have this add function that receives 2 numbers and sum them, and mult function that receive 2 numbers and multiply them, and this formula function that is composed by add and mult functions. And notice that even though the formula function accesses something outside of itself, it's a constant, so it's not gonna cause or be affected by any side effect, so it's still deterministic. And notice that I say that there are no access to variables in functional programming, pure functions, only immutable constants. And it may sound kind of weird, so let's talk a little bit about immutability. So when you're using immutability, a value can change after it's created. So if you need some change in a value, you just create a copy with it with that change applied, and don't sweat it if you're wondering what are the performance implications of that. It's usually not the concern of the programmer to solve it. It's usually something to the compiler to solve it, or the runtime, or any other thing that you can blame besides yourself. And so when you're using immutability, the functions get easier to reason about because there's nothing tricky happening behind the scenes somewhere. You're sure about it. And because of immutability, you're able to use referential transparency. So here I'm showing a small example of what is a function that uses immutability. So we receive an object there, and the function says it activate that object, whatever it means. And instead of changing the value of active attribute of that object, we're returning a new object which is a copy of that older one, plus a new attribute called active with the value of true. So I said another thing there called referential transparency, and different from immutability, this is something people coming from outside functional programming don't know about, or I don't know, think the name is weird. So let's talk about referential transparency. So you get to referential transparency when you call for a pure function can be replaced by its returned value. It's something that is uncommon in OOP because if you can't have referential transparency when you have internal mutable state. If you have like private attributes, it's not something that you call a method that changes a private. It's not, you're not able to reproduce that just replacing the call for that method, creating a new variable, because that change is internal. So because of referential transparency, it makes it reliable to use higher order functions. And notice that when I'm talking that your functions is gonna have a referential transparency, it doesn't mean that you have to make this replacement yourself. It means that your functions should be thought in a way that they can suffer referential transparency. They should be safer to suffer referential transparency. So here I'm gonna show a small code with an example of this process of replacing stuff to prove that referential transparency happens to these functions. So again, we have those add and multi functions that do the same from the previous slide. And we have a code where we call them. So we add 2 to the multiplication between 4 and 10. And then we begin to replace each of these calls in this code. So we replace mult with the actual content of the mult function. And then we replace add with the actual content of the add function. And then we consider the operators to be functions as well, and replace them. And you see that the final result, not just saying about the returned value, but all the other side effects that might happen in the outside of this function remain the same. So we're sure to affirm that add and mult are functions that have referential transparency. Okay, so I say this lot of junk here just to make it to the point of, okay, referential transparency makes it reliable to use higher order functions. And what are higher order functions? So higher order functions, or HOFs, they are functions that either takes functions as args, return functions, or both of it. And it's something that's only possible when functions are first-class system. And even though there are some languages that allow something similar to higher order functions without functions being first-class, it's not exactly the same, but it's not a hill I'm willing to die on. So let's move on and not get too deep on that. And because of the higher order functions, we they allow the existence of closures in the language. So here we have two small examples of high order functions with the mult functions written in a different way, which returns a new function and does the multiplication inside of it. So in the second line where we create this new function double, the call for mult passing just the 2 is going to return a new function that's going to return everything that you pass it multiplied by 2. And then we have an example of the map method of the array class, which is also a high order function because it receives a function as a parameter. So that's pretty much it. And you can see that it's safer to use high order functions when you know the function has referential transparency, because you know there's nothing else that the call side that's going to call this function should be expecting to happen. Okay, I said that, and I got to the point of closures. So some people never heard about closure or know it by name, but don't know exactly what it is. So let's talk about closures. So closures are a function that has access to the scope of the outer function where it was created. They increase code expressivity when you're composing new functions. And they allow the use of currying and partial application, but those are two other concepts in functional programming that are not that basic, because some people even confuse what is the difference between currying and application. So let's not go there today. So I'm going to show an example here of closures. So we have, for example, the mult function that we implemented in the previous slide. It is a closure because the most internal function that's returned by mult has access to the variable a that is from the scope of the outside function. And also we have this compose function that is a closure function because it has access to the array of functions that is passed through the first time you call it. And it increases expressivity because when you're using closures to compose it, you don't need to create an explicit reference to the argument that you already passed. So for example, when we create the formula function, you don't need to have a reference to the second argument of add or the second argument of mult. They're implicit for you, and when you call formula, it's gonna behave as you created manually a new function that receives x as a argument and call add and mult for you. So okay, I talk a lot about approaches that functional programming, and you might be wondering, what about side effects or mutability or non-determinism? The word is a mutable place, and you're absolutely correct, and you have to do it somehow. So okay, let's talk about side effects and non-determinism. And let's be honest here, I'm gonna say something that people usually don't get right, but let's be very honest here. A side effect-free program is a useless program. There's not a single useful program that is side effect-free. And if you're trying to think of a useful side effect-free program right now, here's some examples of things that are considered side effect-free that people don't usually think about it. So some examples of side effects are showing something in the screen, or updating the database, or sending an AJAX request. And yes, the simple fact of printing something to the screen is a side effect. You're mutating the state of the screen, and it might sound silly, but especially for people from the front end side, it's easier to understand that it's a mutability, because if you add something to the DOM or the screen and you need to change it, you got to make sure that it's actually rendered, or it was removed before and you're going to begin a clean state. So yes, showing something in the screen is mutability. So how do we deal with side effects in functional programming? We got to deal with it somehow, right? So I usually follow 3 small rules, which are minimize it, isolate it, and then postpone it the more you can. But okay, I didn't say too much, but how do we actually work with it? So let's translate these rules. So again, starting over, side effects and non-determinism. So minimize it, make the vast majority of your functions pure, and if you have some side effects, put it in some small and simple non-deterministic function. So isolate it, put non-determinism and side effects in higher order functions that's going to receive pure functions as parameters and call them. I'm going to show an example of this soon, bear with me. And postpone it. I mean, evaluate the non-determinism as late as possible in a way that you can compose possibilities of non-determinism before actually run it. So I'm going to show a code here showing how this applies. So I have a small example here with I don't know, real world example where we fetch a user from an API, and we either show the username in the screen, say success message and the username, or saying error message and the error message. So notice that I have two comments to separate what is pure and what is impure in this function, in this code. And you see that the pure functions is the majority of our codes. So we have the compose function, which is pure, the promise, the render success that just receive a message and returns it with a tag of success message, and the render error that just receive a message and returns it with the tag of the error message. And we have the get username that receives an user and returns the name of the user. And then we use the compose function that create a new function called handle success, which is also pure because it's a composition of two pure functions. And we do the same with the error. We have the get error message, which just receives an error and returns the error message. And we create the handle error the same way we did for handle success. And these are all our pure functions. So most of the, I don't know, the important part of what our program does is pure. And we have a single impure function called fetch user that is non-deterministic because it depends on the external service. So it's gonna call the user endpoint or some API, and then gonna parse it to JSON and return it. So this is non-deterministic because from the call side, you can't know if this function is gonna be successful or not. And then we're gonna compose all of these other functions to create the main program, which is also non-deterministic and impure, to create the whole flow of our app. And you see that the most important part is impure. And if you're wondering why promise is not impure, because the promise function, that is the second function of this file, if you're wondering why this is not impure, because it actually deals with an impure data structure, which are the promises, I'm gonna say you that some people even consider that it's kind of cheating. That it's cheating the file that it's not actually pure. So it's not cheating. It's actually pure because when you call promises, it's always gonna return a function. When you call that function that's returned by promises, that new function, yes, that new function is impure. But the functions, the promise function itself is pure because it's always gonna return a function. This is something that is visible if you ever use a Redux thunk. The thunks are actually pure functions that just return a new function. Okay, so we went all over this, and the whole flow of this talk was we went from pure functions to immutability, to referential transparency, to high order functions, to closures, yada, 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 how to isolate side effects. And if you ask me, what is the one factor that made it all possible, reliable, and understandable? What is the one thing that makes it possible to grasp functional programming? I'm gonna say purity. If you understand purity and what are the implications of using purity and pure functions in your code, all of the other concepts is gonna be like I don't know, a domino that once you understand one step, all the other ones are gonna click because you have the limitation of purity and you gotta find pure solutions for that problem. And this is the gist of what I wanted to talk. So what about monads? So being honest here is the fact that everybody that makes a talk about functional programming is legally enforced to make at least one joke about monads. So here it goes. So as the other joke, and actually the truth says, monads are the monoids in the category of endofunctors, but I know it sounds too academic. So let's try to make it better. So monads are composable computation descriptions. I think it makes it a little better, a little easier to understand, but I think we can make it better. Okay, so let's say that monads are like onions. I think it's clear, right? I mean, there's no way to not understand it. But let's try to make it even better. Okay, so monads are actually, they're kind of like burritos. And right now, I might have gone too far. So I'm going to stop here and say that even though they're all those at the same time, you don't actually need to understand monads before beginning, and that's fine. A lot of people get afraid of learning functional programming because they think that there are some crazy concept like monads and monoids and functors and applicatives and stuff that is hard to grasp. And don't sweat about it right now. Focus on purity, and all the other things are gonna click for you. So I'm gonna leave some references about how to start in functional programming and functional thinking, about how to understand what the actual freedom that the limitations from functional programming gives you. And I guess that's it. I hope it was easy to show that purity is the key of everything, and you should focus on understand that. Thanks it, everybody.